Hi everyone, this is CJ Vignesh, working as an assistant professor in KPR Institute of Engineering and Technology. Today in this video, we are going to see a motor design and optimization using a JMAG-Express. For designing and motor design, so I have chosen the axial flux motor topology for designing, and we are going to design this axial flux motor in a JMAG-Express, and we are going to analyze the performance of a motor. And also we are going to see how the optimization technique can be utilized from the JMAC Express, and we can design the motor topology. So what is axial flux motor? So actually the axial flux motor is an axial flux flow between the stator and rotor. This structure of the axial flux motor will be like a disc shaped structure. So it is like a stacked structure. So we will have a stack of stator which will be parallel with the rotor. And this axial flux motor having an high torque density comparing to a radial flux motor, and we have a short magnetic flux path between the stator and rotor. And normally this type of motor can be suitable mostly for an electric vehicle applications, drone applications. And the weight of the axial flux motor will be very lighter and comparing to a radial flux motor. So we are going to see the topologies in axial flux motor structures. So first structure is a dual stator single rotor structure. That means so we will have two stators. In between that we will fix the single rotor. So that is the first topology, and second topology is single rotor, and we will have a dual stator. That means a rotor will be present in the center, and we will have a double in the both sides we will have a status, so that we call it as single rotor and dual stator. And multi-stack is like combining an stator rotor combinations for n stacks. That means I can add multiple stacks, so which cannot be in one or two, so I can add more number of stacks if I needed more torque. So for that we are going for a multi-stack type of motor. So normally the permanent magnet which will be aligned in axial direction with the stator surface, and we are using a JMAG Express software for design. So why we are choosing a JMAG Express for designing means, so this JMAG Express is having a predefined template, so we can perform the design very fast, and we can calculate the EMF or efficiency or torque very quickly, and we can integrate this JMAG Express with a JMAG Designer. So Designer is a three-dimensional analysis software. So we can directly import the two-dimensional. The normally we are doing a JMAG Express with a two-dimensional analysis, so which can be transferred to the three-dimensional, and we can see the three-dimensional flux flow analysis also in the JMAG Designer. So this is the advantage when we are going for a JMAG Express. JMAG Express, so we can use nearly and seven type of permanent magnet templates is available in the JMAG Express. So first is IPM, interior permanent magnet motor type of material can be motor can be used in the JMAG Express software. So second type which we can choose and design is as a surface permanent magnet motor type, and we have an induction motor in the JMAG Express. That is wound field type of synchronous motor can be designed in the JMAG Express, and also we have a capability to design the synchronous reluctant motor as well as axial flux motor type. So as we all know that we have different configurations, so which can be directly chosen in the JMAC Express by default, and you can create the template. So the JMAC Express is having capability to generate a template, so which is already defined in the JMAC Express itself. So first step, when you are opening in JMAT, so here you can see the selected types. So we have seen the different types, right? So in that we are going to select axial flux motor type. And second step is we have to select the scenario. So scenario means, so what is the performance? So I'm choosing an axial flux motor, and now I am going to analyze the performance. So either that can be a scenario. So first scenario, so having the efficiency map. So if I'm choosing the motor, I need to perform the efficiency map of the particular motor, means I can choose the machine characteristics efficiency map. So if I'm going for a thermal behavior analysis, so I can select the mechanical characteristics efficiency map with respect to the temperature dependency. Once you are selecting the scenario, so I can click OK. So once you are clicking, your template will starts to open. So which will open like this. So the complete scenario will be like this. So it will have a template which will having in all the structures. So here you can see. So now the file is getting opened here, and you can see that you will have a file options. So now I have opened the JMAG Express. So here you can see file in the right side. You can select a new file, open or save, or like that. You will have a different scenarios. So the scenarios which you are selecting will be appearing here. Okay, and the dimension. So first thing you are going to design the Axial Flux motor for a particular applications. So I am choosing the Axial Flux motor configuration. So if I need to optimize, so if I'm having all the input parameters, you are going to feed all the input parameters like number of poles you are choosing for a rotor and stator, and then air gap between the stator and rotor, and then stator dimensions. So what is the outer diameter of my stator? What is the inner diameter of my stator? And yoke thickness. So what is the yoke thickness you are giving? So this is your yoke thickness. So you can see that this is the yoke thickness. So if I'm increasing the yoke thickness, the automatically the thickness will vary. So and then coil width. So what is the coil width? So what is the width of the each coil? So this is what we are going to give in this parameters. So once you are selecting all the parameters, so you can go for a material. So you are selecting a material, so you can see the n number of material structures. So we have a configuration like stator and rotor. For the rotor materials and what is the temperature around the motor is going to operate. So that you are going to feed. So and then stator material. So what are the for a coil? Similarly for a core materials. So you can select the materials from the library itself. Otherwise, you can create a new material and you can feed that and you can simulate that. So it having a capability to give you a new material. So you can create and then you can simulate that material itself. Okay. So you are selected the dimension and then material. You can go for an winding parameters. So in this winding, you have a different input types. So you can select this input types. So you can see that if you are having a number of turns and wire size is known to you or you have calculated that, you can directly select the turns and wire size and you can feed only the turns and then wire diameter. So it will calculate the maximum fill factor automatically. Okay. So if you are defined with our turns and wire size, so you can select the turns and wire size. So turns I'm choosing 20 turns and diameter is 0.6. So once you are selected, you can go for a drive cycle. So what is the maximum voltage you are going to use for your motor to drive, and is the maximum current value which you are going to use, and what is the maximum speed, and then what is the losses, and then operating point. So at which operating point the motor will be operating. So you can select all the parameters. So once you have selected all the parameters, you can directly simulate. Okay. So another advantage in the JMAG Express is so you can incorporate this motor into some applications. So that means I am going to use this motor for an in-wheel applications or an mid-drive applications. So I can choose the types here. I'm going to use this motor for an EV applications. So for if you are implementing this motor in an EV application, so you are going to either you are going to directly use as a mid-drive motor or you are going to use as an hub motor. So these two scenarios can be selected if you are going for an application oriented analysis is you are going to done means you can choose the vehicle conditions and you can give all the parameters. Okay. So once you are given, you can go for a run. So it is the direct method which you have implemented and you are going to run. We are going to see is optimization techniques. As we all know that optimization is very important for a motor design. Okay, parameters. So already you have designed all the values. So in that, what is the main functions or constraints you are going to give? So you are fixing a constraint like number of poles and the number of stator poles. So I'm choosing number of poles between minimum value is 8 and maximum value is 60. Okay, so if I am selecting the slot, the number of slots, so which is 18 to 24 means, so this is the minimum and maximum condition you are going to give for an conditions, and then you are going to give the objective function. So what is the objective function? So I am designing the motor, so which has to give a maximum torque density means, so I can select the maximum torque density as an objective function. Okay, so for that, here you can see the objective function. So add objective functions. So here you can see the parameters. These are the parameters. So now I am choosing maximum torque density. So that just double click, you will get the expression here. Okay. So I'm going to optimize this motor for a maximum efficiency. So I'm choosing maximum and give the condition. So what is the name I'm going to give and title. So once you have given all these parameters, so you can give OK. So now you have selected the constraint conditions, objective functions. So and then you are going to give the initial cases. So initial cases already I have created the design. So this is the initial case, and then I'm going to go for an optimization. So this options. So what is the optimization technique I'm going to use? So optimization engine. So you can select genetic algorithm or a multi-objective optimization algorithm or a genetic algorithm with surrogate optimization or multi-objective optimization. So here I have given the objective function only one, so I can select an surrogate genetic algorithm or genetic optimization. Okay, and number of generations. So what is the maximum number of generation which I need to go? And then you have to choose a population size. Your population size has to be considered based upon the number of constraints you are choosing. It has to be more than the chosen constraint. Okay, that means if you are choosing two constraints, the population size has to be more than that two value. Okay, so once you have completed all this, you can check that whether your given optimization is correct or not. Okay, so if your optimization technique is correct, message like this, there is no input error. So if you are having any error, so it will indicate that it is having error. Okay, so once all the parameters are right, you can go for a submit. It will starts to generate an optimization. Okay, now you can see that the optimization is getting simulated. So once simulated, you will get the output. Now you can see that motor has been run by a JMAG Express. So here you can see the different scenarios. That is, so I have chosen the dimensions, right? So here the three scenarios which is getting run here. So which is for different parameters. The number of coils which so we have given the optimization. So for that number of 12 number of poles, 8 number of poles which is run, and it is giving the output. So based upon that, so you can optimize the output can be obtained. So for 8 out, so maximum torque, so which I'm getting is 8.3 for the 12 poles. Okay, so this will be the optimized output when you are taking as a comparison, and you can see that. So what is the maximum output and what is the maximum efficiency you can get. Similarly, so when you are seeing the results here, you can see that first case, that is 12 volts. So you are getting a maximum efficiency of around 96 percentage. But when you are seeing the second one, the maximum efficiency is around only at 94. And also the torque developed in the 12 volts is around 110 Newton meter. But the torque is around only 60 Newton meter in the second case. Okay. So similarly, the maximum torque versus output power. So the maximum torque which here you are getting is around 145. But in this scenario, the maximum torque you are getting is around only 90. And the output power, you will have a some different changes here. So as we are selected only the characteristics or machine characteristics, so we are getting that. So if we are going for thermal characteristics also, we will get the similar like this graph for the thermal characteristics also. So that's all about the video today. Thank you for watching.